Hi, everybody. Welcome to our 6.3 guided notes, and this is our last notes of the semester, so congratulations. We are almost there. All right, so today we're going to be talking about orbits and Kepler's laws and energy when we have a lot of particles. So we're kind of just getting all the last things that we haven't covered so far. So first we're going to talk about orbits, and if you look down on your paper right here, you can see that there's an image and here's Earth in the middle, and then there's several different orbits. And just so you know, this is not the entirety of all of the orbits, and the AP test is not actually going to ask you about specific orbits, but it's, I think, important to understand what is happening, especially if you want to go into some type of engineering that is going to be making satellites. This is a really fun thing to understand. So we have first the low Earth orbit, and the low Earth orbit is good. Like I just put a bunch of facts here that are hopefully interesting for you. So good for high resolution Earth observation because they're closer. The International Space Station is there, and then satellite constellations for internet. So our internet is often in the low Earth orbit, and this is the easiest thing to get a satellite into. But your atmosphere is still there, and so you're going to have a lot more friction on these satellites as they're going around. So the next one in your image there is MEO, which stands for medium Earth orbit. And our GPS is in this one. It's kind of a balance of being close, but also it's not as expensive to get into that as it would be to get into the high Earth orbit, which is the next one we're talking about. So the next one, sometimes you'll hear high Earth orbit, but one specific type of high Earth orbit is the geosynchronous or geostationary orbit, and that's essentially this far out, so 35,000 kilometers, and it's a lot more expensive to get there, but it can continually observe the same area, and so essentially it's going to orbit Earth as Earth turns around. It's going to be over that same spot. And so that's how far out you need to be in order to do that. And so that's really helpful for forecasting, broadcasting, for weather monitoring is really helpful. And so just a lot of different things going on here. We also have polar orbit that I've listed here that, or that's in your image, that is observing things at the poles, and so also all sorts of things you can do in space. There's also a highly elliptical orbit. There's all different types of orbits, but we care in this course a lot about orbital energy, orbital velocity. We talked a little bit about that in our last lesson, so hopefully you remember that. But this is an important thing to understand. So how can we change our orbital altitude? And to be clear, typically when somebody's sending a satellite into space, they're going to send it to the orbit that they want to. Generally, you're not going to be in one orbit and then boost over to another orbit, but for the sake of physics problems, we want to understand how you could do this. So in this picture right here, it says force backwards. Really, we're thrusting out of the back of the rocket, which, as you can imagine, creates a forward force on the rocket. And if this happens, then we're going to be getting into a larger orbit. But the interesting thing about this is it says thrusting from the back seems like you will speed up, because if you could imagine, if you're in a rocket and you shoot out of the back, you're like, pew, speeding up. But it'll actually put you into a larger orbital radius, which ultimately slows you down. And that's what's weird. And the reason why is because your kinetic energy is going to decrease. So the further out orbit that you are in, relative to Earth, you will have a slower velocity as you're orbiting. And so because of that, you have a decrease in your kinetic energy. Whereas if you are thrusting out of the front of your rocket and essentially like slowing it down as you might consider that, that will put you into a smaller orbit here. That's an ugly smaller orbit. There we go. Smaller orbit. And that will increase your kinetic energy. So ultimately you'll be going faster if you're closer. And if you think about that, hopefully that makes sense, because you have more of a force due to gravity from Earth. And so that will enable you to have more kinetic energy there. Okay, so let's keep going. There is a dude named Kepler. He came up with a few laws. I apologize in your notes that you don't have a period after the word heavens. I put one there. You can put one there too if you want. So there's three laws that he formulated when he was studying the heavens. So the first one is the law of orbits. We're just talking about orbits. So all planets move in elliptical orbits, and not just not just all of our planets, like anything, any type of body that is orbiting a star, or any type of body that has a central mass that is much bigger than its mass, is going to move in an ellipse. And that star, or in our case, the sun, is at one of the foci or focuses. And so you can see in this picture right here, make it my highlighter. So this F1 and F2, those are each a focus. And so for our particular situation, you would have the sun at one focus, and then random blue dot is at the other focus. There's nothing actually there. It's just mathematically something that's existing. And so then you would see the orbit of a planet is going around that. Whereas if we have, for example, in this picture, we have Halley's Comet. So the sun is over here. So that's highly elliptical. But even with that, our sun is going to be at one focus, and then there's something else at the other focus. And I want to highlight a few different things here. And a few of these terms are important so that you will be able to do problems regarding orbits and ellipses and things like that. So one of them is this variable A, that's from the center to the furthest point right here. And that is our semi-major axis. And then this other bit over here, B, the smaller from the center to the closer point on that ellipse, is called the semi-minor axis. And then we have the words apogee and perigee. Apogee is the farthest, oops, get back here, notes. The farthest point from in the ellipse, and so in this one over here, that would be your apogee because it's the farthest from the sun. And then the perigee would be the closest. And so that would be right here because you're closest to the sun at that point. And so, wow, that looks like dosist. Let's try that one again. Sorry, guys. Closest. All right, cool. Next one, law of areas. So this one's kind of interesting. And before I get too much into this, I just want to let you guys know that recently, we have a note right here. Recently, the AP Physics Mechanics doesn't expect you guys to know the first two laws. You do need to know the third law, but there's little pieces in the first two laws that they will sometimes bring up. Like you do need to know what these terms, semi-major axis and where did my semi go? And semi-minor axis are. You do need to know essentially what an ellipse is. And for the law of areas, I'm going to tell you about it. Even though it's a law that you don't need to know necessarily, you do need to be able to use these concepts of angular momentum. And so what's happening here is that angular momentum, as you would expect, is conserved. And so what's happening here is that we have our sun, and we have over a period of time, your planet is going to swoop out some sort of area. And if you draw a triangle, or almost triangle, a line that connects from the original place to the final place in one period of time, this triangle would be the exact same area that if that same planet on that same orbit, let's say that it started at a point here, and then it had the same period of time there, whoop, the triangle that would be made here would be the exact same area. So essentially the purple area would equal to the black area. And what's happening there and why we care about angular momentum is that we have a much faster velocity over here and a much slower velocity over here. And that's because of our force due to gravity. And so as we're closer to the sun, it's going to be swooping out a lot faster. But our angular momentum is conserved as we go around. So our radius is getting a lot bigger. So our radius is, oops, let me just point it out here. So our radius is bigger here, meaning that our velocity is smaller, whereas our radius is much smaller, meaning that our velocity is bigger. And the mass would just be the same for both. And so that's how our angular momentum is conserved, and that's what that means to have the law of areas there. And all right, so let's continue here. In elliptical orbits, the system's total mechanical energy and the satellite's angular momentum are constant, but the gravitational potential energy and the kinetic energy can each change. So essentially, at these different places, our potential energy and our kinetic energy are changing from here to this point over here. So it's not the same here as it would be over here, but the total mechanical energy is indeed the same. Whereas in circular orbits, the system's total mechanical energy, gravitational potential energy, and the angular momentum and kinetic energy are all constant. And hopefully that makes sense, because if we have a circular orbit, then our radius in all points is going to be exactly the same. And so then our velocity at all points will be the same. And therefore, all of these things are constant. So elliptical, we're going to go slower as we go away and then faster as we loop past the sun. Whereas circular, you just have the same thing going the whole time. Okay, so next law from our dude Kepler, the law of periods. This one is important. It's very likely they're going to ask you to derive this on a test. So make sure you know this. So the general thing for this law is that the square of the period of any planet, or as we've discovered, as anything orbiting a big central mass, is proportional to the cube of the semi-major axis of its orbit. So see, look, we need to know what the semi-major axis is in order to know the third law, so it's good to know those other ones. All right, so we are going to derive this. Essentially, this is a formula that we're going to derive, and we are going to derive this using circular motion. I know that it says elliptical. Where does it say? Well, it says semi-major axis, and we know that they move in ellipses, but all of our planets actually have almost circular orbits. And so we're going to do an approximation of this and prove it using circular motion. There is a proof using elliptical orbits, but it is beyond the scope of this course. So we're not going to worry about it because that circular approximation is actually really quite accurate for our planets. All right, so we're going to start with, let's change colors. All right, we're going to start with F equals ma. And if something is moving, look at that awesome circle. If something is moving in a circular orbit, we know that we have the force due to gravity that is pulling in towards the sun in the middle. And that force due to gravity is the same thing as our centripetal force. So I could say my force due to gravity is the same thing as mass times centripetal acceleration, because that is the type of acceleration that is causing this force here. And so then let's change around. So we know that our centripetal acceleration equals v squared over r. It also equals omega squared r. I'm going to use omega squared r because I know that eventually I want to get to period, and I know what a period is in terms of omega. So that's going to be slightly easier for me to start with. So I'll say Fg equals, oh, never mind. Let's change our Fg to what we know our Fg to be. Sorry, that eraser is getting crazy. Stop it. There we go. So instead of saying Fg, actually I will change colors. I'll say G, M. So let's be careful about our M. So I'll have the mass of the planet times the mass of the sun all over r squared, and that r is the distance from the center of masses to each other. And this is going to equal to the mass of the planet, because we're talking about the object in question here, times omega squared r. And so at this point, we see that the mass of the planet will cancel out, and I would like to get omega squared by itself. So omega squared is going to equal to all of the stuff that I have over here on the left-hand side of the equation, also divided by that r squared. So I'll have G mass of the sun divided by r cubed. So here we are. And then we remember, hopefully, that our period equals 2 pi over omega. And so we have omega, or we have omega squared, so we can plug in what we know there. So we'll have t equals 2 pi times, I'm just going to square root this all in one go, and it's going to be the reciprocal of that. And so I'll have r cubed over g times mass of the sun. And then from here, I'm just going to square both sides of my equation. So I will square all of this, and I will square all of that. So I'll have t squared equals 4, oops, that's a 2. 4 pi squared r cubed over g times mass of the sun. And you can see that we ended up with what we were going for. And so make sure that you, first of all, understand how to do this and how to derive this, because that, like I said, is a common thing that the AP test will ask you to do. But you can also see right here that we essentially have a big constant number times our radius. And so this is going to, and you notice also that the mass of the planet canceled out. So it does not matter how massive your planet is as long as it's less massive than your sun that it's orbiting. And so you just have your t squared is proportional to your r cubed, or your semi-major axis if we have an elliptical orbit, because we, like we talked about, is a close approximation. Cool. So that's this third law. Let's keep going. We're really close actually on these notes. There's not too many notes here. Okay. So sometimes you're going to have more than 2 particles that you need to figure out potential energy between. And so the absolute value of the total potential energy represents the work needed to separate the particles by an infinite distance. So what we're going to be working on here is basically, if I have multiple particles, what is the potential energy of all of those existing with each other? So the way to do that is, first we're going to list all the unique pairs. So if I have particle 1, 2, and 3, then I would have potential energy between 1 and 2. I would have potential energy between 1 and 3, and I would have potential energy between 2 and 3. If we have 4 particles, obviously there's going to be a lot more pairs, or 5, or whatever. Generally, you're only going to be asked about 3 particles, so that's not too hard. And then we would want to calculate the potential energy for each pair. So I'm like, all right, potential energy of from 1 to 2 would be negative g m1 m2 over r1 2. And remember, when it's the potential energy and not the force due to gravity, that r is not squared. So then we'll just continue with the other ones. Should be like, all right, u1 3 equals negative g m1 m3 over r, the distance between 1 and 3, and then u and 2 3 is the same thing. So negative g m2 m3 over r from 2 to 3. So once you figure out each of those, then you just add them all up. And so I'd be like, u1 2 plus u1 3 plus u2 3 will equal u total. And so this is just the sum of all of your pairwise potential energies. And then the total energy, if you were ever asked that, it would be this plus the total plus all the total kinetic energies. So essentially you're just adding up all of the energy. But if there's still, then, and you want to know the total energy, then of course you just add the potential energy. And so this strategy is important also because very soon we're going to be talking about electrostatic potential energy, and it's the same type of thing that we do. Okay, last little bit. An example, we have 3 particles. They're on an equilateral triangle. Each side is 30 centimeters. And we want to know the potential energy between them. And so I'm like, all right, potential energy between particle 1 and 3 is negative g. The mass of one of them is 5 grams, so I'll put 0.005. Mass of the next one is also 0.005. The distance between them is 30 centimeters, or 0.3. And so I find out that this is negative 5.56 times 10 to the negative 15 joules. But then you might realize that all 3 particles are exactly the same. And so you would just multiply this by 3, and you would find out that our total potential energy is negative 1.67 times 10 to the negative 14 joules. And that is it. Good job today. We are all done.